In this video for section 2.1, we're going to start with some vocabulary. Our first definition is for a relation. A relation is any set of ordered pairs. They could be words, they could be numbers, it could be a mixture of both, but as long as you have two values and some sort of relationship between them, that's a relation. The set of all first components of the ordered pairs is called the domain. Sometimes we call the first components the input values, and so the domain would be the set of all possible input values. The set of all second components is called the range, and sometimes we call the second components the output values. So in example 1, it says to find the domain and range of the relation. So we have a set of ordered pairs here. It looks like the input values are names and the output values are numbers. So we're going to start with the domain. And when we write the domain, you'll see this in the homework, they're going to put a squiggly bracket and you're going to type the values in the squiggly bracket. That indicates that this is a set of values. Or a set really just means it's like a group. So a group of, in this case, names. So I'm going to list the input values here, or the first components in my domain, and that's all of the possible input values, so all of the ones from the points that I have. And then I enclose that in the squiggly bracket. Now for the range, I'm going to list all of these second components. Now you see here in this set, I have some second components that are repeated. So 95 appears in 2 different points. That's okay. When I list it in the range, I would only list that number once. So I don't write 95 twice, I only write it once. Then I have a 90, and then I have 82. Again, that appears in 2 points, but I only need to list it once in the range. So that's my range, 95, 90, 82. So next you should try checkpoint number 1. Do this in your notes, check your answer, and then move on with the rest of the video. Our next definition is for a function. A function is a special type of relation so that each element in the domain corresponds to exactly one element in the range. In other words, it can't correspond to more than one element in the range. So in example 2, we're asked to determine whether each relation is a function. Now what I'm looking at here is I'm looking at all of the elements in the domain, or all of the first coordinates, and I'm seeing if any of them go with 2 different second coordinates. So here I have 1, 2, 3, and 4. Each one only has one value for a second coordinate. So this example A is a function. Now looking at B, it's a little bit different. I have the point 6, 1 and 6, 2. 6 has 2 different values for outputs, 1 and 2, and so that makes it not a function. I don't even need to look at the other points. If I find one input value that has more than one output value, that automatically makes it not a function. So next you should look at checkpoint problem number 2. Do this in your notes, check your answer, and then move on with the video. Our next topic is function notation. And we have this f with x in parentheses, that's called function notation. And we say f of x, or sometimes f at x. Usually we use of, but you might hear at. And that represents the value of the function at the number x. So another way to think of it is whatever is in the parentheses, we're plugging in for x. So now we're going to look at example 4. It says if f of x equals x squared plus 3x plus 5, evaluate each of the following. A is f of 2. So that means we're plugging in 2 for x. So I'm going to replace every x here with a 2. So we're going to have 2 squared plus 3 times 2 plus 5. Now in this case, I'm just going to do this math and I'm going to end up with a number answer. So order of operations, exponents first, then multiplying, then adding. That's going to be 4 plus 6 plus 5, or in other words, 15. So f of 2 is equal to 15. For part B, this one's a little bit more complicated. Now I'm plugging in x plus 3. That means I'm replacing every x with x plus 3, and I need to plug it in parentheses in order to get the math right. So that's going to be x plus 3 squared plus 3 times x plus 3 plus 5. Now, we talked last week about what to do when you have x plus 3 squared. It's not x squared plus 9. You have to multiply x plus 3 times x plus 3. So I'm going to use FOIL on that. That's going to be x squared plus 3x plus 3x plus 9. Now for this, 3 times x plus 3, I'm going to use distributive property. So that's plus 3x plus 9, and then I still have this plus 5 at the end. Now I need to combine everything together. So we have x squared, we have plus 3x, and plus 3x. That's a total of plus 9x. And we have plus 9, and plus 5. 18 plus 5 gives me plus 23. So this is my answer. If I plug in something that has a variable in it, then my answer is most likely going to have that same variable in it. So I don't get a single number answer like I got for part A. And lastly, for part C, now I'm plugging in negative x. So for this one, what's going to happen is I need to think about what happens when I'm doing things with negative numbers. If I have a negative number and I square it, I know it's going to become positive. So whatever x is, negative x times negative x is going to be the same as x times x, or just x squared. Then I have plus 3 times negative x. I can simplify that to minus 3x. Positive 3 times negative x is going to be minus 3x, and then I just have plus 5. So again, because I was plugging in something with a variable, my answer is going to have that same variable in it. So next you should look at checkpoint problem number 4. Do this in your notes, check your answer, and then move on with the video. What we're going to do next is look at one of the problems in the exercise section of the textbook, and we're going to look at this because there's going to be a similar problem in your homework. This is exercise 105 from the problems in the end of the section. It says a company that manufactures bicycles has a fixed cost of $100,000. It costs $100 to produce each bicycle. The total cost for the company is the sum of its fixed cost and variable cost. Write the total cost C as a function of the number of bicycles produced X. Then find and interpret C of 90. So this is, as you can see, an important business application of algebra. So we're writing the cost function, which is going to look like C of X. C, capital C, followed by X in parentheses. X is our variable, because we want to write the cost C as a function of the number of bicycles produced. So C of X. Now we have our fixed costs of $100,000. Fixed costs means that they don't change, they're fixed. So that's just $100,000. That's a flat cost. It doesn't matter how many bicycles I produce, I'm going to have to pay that $100,000. Those are usually for things like executive salaries, rent on buildings, and things like that. Now, it also costs $100 to produce each bicycle. So that means for each bicycle produced, I have an additional cost of $100. So I'm going to multiply the number of bicycles that I'm producing by 100 to get that part of the cost. If I produce 5 bicycles, it's going to cost $500. 10 bicycles would cost $1,000. So that part of the cost is 100 times x, because x is number of bicycles. So this is my cost function, 100,000 plus 100x. The second part of the problem says to find and interpret C of 90. So remember, when I have a number inside the parentheses, that means that it's a number that I'm plugging in. So I'm going to plug in 90 for x. So that's going to give me 100,000 plus 100 times 90. Then I would do the math here, 100,000 plus 100 times 90 is 9,000. So that's a total cost of $109,000. So for interpreting, this is the cost. 90 is the number of bicycles. So that means it costs $109,000 to produce 90 bicycles. The last thing we're going to talk about in this video is the vertical line test. The vertical line test, we look at vertical lines across the graph. And if any vertical line intersects the graph in more than one point, the graph is not a function. So what we do is we think about, okay, if I were to draw a vertical line, is it going to cross the graph in more than one place at any point? So looking at A, the answer is yes. That's not a very vertical line, but if it were a little more vertical, there would be 2 points that the line would cross the graph, and that makes it not a function. For B, if I think about taking a vertical line and drawing multiple ones or dragging a vertical line across the graph, each vertical line is only going to cross the graph in one point, and that means it is a function. It is not possible for any vertical line to cross the graph in more than one point. Same thing for C. This one's a little more of a bowl shape, but any vertical line is only going to cross the graph at one point. So that means yes, it is a function. For D, it is possible to draw a vertical line anywhere in this area, and the line is going to cross the graph in 2 points. So that makes it not a function. So next you should look at checkpoint number 6. Do this in your notes and check your answer.